Okay, welcome back for the fifth part of the algorithm section. So first thing you'll want to do is go get the PowerPoint from the Canvas module. Let me start sharing here. All right, so Intro to Algorithms Part 5. And hopefully you've completed up to number 16 in the Rosalind problems, that is the clump finding algorithm. So what happens when you extend that clump finding algorithm to analyzing the whole E. coli genome, for example? You might find, or in this case, you would find that there are lots of clumps that are defined by 500 base pairs and have a 9-mer that occurs 3 or more times, right? So that was sort of a definition of the size of how many times a 9-mer would have to occur to be very unlikely to happen by chance. So it actually happens that there are multiple clumps like that, and you might go ahead and look for the most extremes for that. But it's at this point just not, it becomes unclear whether the simple motif finding frequency, or finding the most frequent words basically, is going to give you the best solution all by itself. And so this is where you sort of separate, or a pure computer scientist might say, there's just not enough information here, right? You can't define where the origin of replication is just by having frequent words or that are unlikely to happen by chance in a small region. And so basically we need more biology, and that's where bioinformaticians come in. So ideally, right, people who get jobs as bioinformatics specialists are bridging the gap between the biology and the computer science. It's important to know how to talk not only the computer science side, but talk to the biology side, and to have, most of the people in this class have the biology background, and you're mostly learning about the computer science side. But when you get out into practice, you may be, so for example, when I went into my postdoc, it was a little bit the other way, where I had a bioinformatics background, but I was in an environment with a lot of computer scientists that didn't have biology background. And so that is the sort of unique marriage of what makes a bioinformatics. So in this case, where can we get more biological information? So actually, let me just, I need to switch displays. There we go. So, right, we're trying to find the origin of replication, and this is just a pretend bacterial genome where it's double-stranded. One strand is blue, one strand is green. They go in opposite directions. And if we think about how this thing replicates, there we go. Right, it's going to sort of have a directionality to it, where on the blue strand, this 5' to 3' going from left to right, the DNA polymerase is actually going to build the new strand in this direction, okay, on the blue strand. So we call that the reverse strand. It's sort of building it backward. And then on the other strand, it's going the other directional, because DNA polymerase, again, is unidirectional. Okay, so the reverse half strand is double-stranded almost all the time, because this process of DNA polymerase replicating actually goes really quickly in that direction. So what's happening though on this, since we have biology backgrounds, most of you know that's called the lagging strand, but it's also sometimes called the forward strand. So forward because the actual DNA direction is that way, even though the polymerase has to go in this direction. So you get these Okazaki fragments, right? So it has to, continually keep starting, but it has to wait for the DNA to open up far enough before it can start building those strands. And so that forward strand or lagging strand spends a lot of its time during replication as a single stranded piece of DNA while it's waiting for it to open up and then, stick in the next Okazaki fragment. So that part of the DNA on the forward strand is single-stranded for most of its life during replication, of course. Okay, so how does that help inform the computational problem? Well, there's a mutational bias for cytosine to mutate to thymine. So that's, first of all, that happens whether it's single-stranded or double-stranded. But when it's single-stranded, that deamination rate is 100-fold higher. So then what happens is, right, if we just focus on the blue line, the outer strand here, this forward strand, as we're going along the outside, because that is going to be single-stranded on the blue one for most of the time, or a lot of the time during replication, those C's have a really high mutation rate to T. So on the blue strand here, as we go around this way, we're losing T's, but there's no change in G because the G is not affected by this increased mutation rate, okay? And the C on this side, whoops, going that way around, right? That's on the green strand, so that's actually going with the direction of the polymerase on this side. So this is it's double-stranded as it replicates the green strand, and it's single-stranded as it's replicating the blue strand over here. If we look at the other side over here, right, because replication is going in both directions, now the blue strand is going in the direction of the polymerase, and so the G's are actually fine, but it's the C's on the green strand, right? Because over here green is forward or lagging strand, and so the C's on the green strand are getting converted to T's. Okay, so and then the C's over here are not changing. So if we look at what that looks like in terms of the GC dynamics, right? As we go this direction around, we're losing C's and we're not changing G's. So if we took G minus C, we would see that there's this number is increasing, okay? Until you get around to this point where now we're sort of halfway around and we have the other kind of dynamic going where the green strand would actually be losing C and G minus C is going to be decreasing over here. Just to be clear, we're not act like this. So you keep C and lose G on the blue strand. That's not because there's an increased mutation rate of G, right? That's because the C on the green strand is being converted. In order to match it, you end up getting an A on the blue strand. So you're losing the G's over here. Well, if you sort of do that sort of mental exercise of walking around how replication works, turns out that when you get to this point where the GC has been sort of decreasing on the orange line there, and then it suddenly starts to go up, then you are at the origin of replication, right? So backing up a step. All right, so that part right there is where you've, makes sense to go here, right? You've been going down, 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 and then all of a sudden you start going up, 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 up. Okay, and if we plot that, it looks something like this. And so I color coded these, like the purple arrows are on this genome going along here. So where that G minus C is increasing, and the orange line is going around this way. So that when you stop decreasing and then you start increasing, that is going to be the most likely spot for origin of replication. So in that big pool of Kamer clumps, so from the clump finding algorithm, you know, which of those highly unlikely clumps of binding sites is the actual origin of replication? Well, now we have more biological information to suggest that if we can find the position in the genome that minimizes the skew, so this point right here, where we get that inflection, if there's a clump there, that is most likely the origin of replication. Okay, so that gets you to the next Rosalind problem, which is to basically build some code to find the minimum skew, where the skew is the G minus C. Okay, so question 17. Having internet problems again. Hopefully it survives long enough for the recording. Right, so you're given this sequence and you need to find the points along the sequence that minimize that G minus C skew. And then we're also going to learn to plot this today. Okay, so just taking a look, if we start out at 0 and thinking about how do we want this algorithm to work, every time we see a C, we want to give a -1. Every time we see a G, we want to go +1. If it's an A or a T, we just do nothing. So we go -1. When it sees a G, it goes up 1, 2, 3, then back down, and so on. So we just need to slide along the sequence, add 1 if it's a G, subtract 1 if it's a C. Right. So that shouldn't be too hard. Give you a little bit of pseudocode here. Right, you're just going to build a function, and you know, if you build it as a function, great. If not, you don't really have to, but basically you're going to call the function something like minimum skew, and it's going to take a sequence because Rosalind is just going to give us, whoops, man, sorry. That's all you're going to get for input is one line. Okay. Then we're going to start something called a skew list that starts at 0, right? That's this thing. So our list starts with a value of 0. And then we need to make a loop. Could be something like for I in text, right? That will loop one at a time over whatever the text is, or the sequence, whatever you've called the string of DNA. And if you have a C, subtract 1. So, right, what does that if statement look like? It's something like if sequence at position I is C, something like that. Then add 1 to your SKU list. Okay. Now, are we think about what you're building here, because we need to keep the value, the current value, lined up with the current index. Because so at position 0, the value was 0. And if we call this position 1, I don't remember how the indexing works. It's something that you'll have to work out. I don't remember what Rosalind wants, is what I mean. Yeah. Look, I mean, you'll know based on the practice data whether you're off by 1 or not. So I don't know if, right, the value of at index 0, is it supposed to be -1 or 0? That's whether usually Rosalind tells you base 1 or base 0 indexing. So how do we keep the values, right? This list, this SKU list, how do we keep that lined up with the value, right? We need something like if the sequence is C, SKU list append whatever the current count is. Okay, so like, are we at 0 plus 1 minus 1? So we haven't counted yet. So actually, one way to do this, right? If it's a C, what do we want to do? Let's call count equals count minus 1. And what that also means is we need to, and I skipped over this, initialize a counter before we start doing this, right? We need something to keep hold of the count. So the count starts at 0. And if we do something like SKU list starts at 0. I suspect it, now that I think about it, Rosalind probably wants the first position in DNA to equal index 1. I think that's how it takes it. So in that case, right, now we have a count of 0 at SKU list with index 0. And then in our pretend example here, first nucleotide it gets is a C, so we need to subtract 1. So the SKU list is going to look like 0, and then the first time through it's going to go -1, right? And then we'll want it to go and get the next letter. Okay, this is all inside a for loop. Whoops. And then, right, you need something like LF sequence I, oops. Is G, then the count goes. Okay, remember this notation? Remember, I should have done that up here too. It doesn't matter, should have. It's exactly the same, effectively. It just looks nicer this way. So if the sequence is a C, subtract 1 to the count. Else, if it's a G, add 1 to the count. And then we don't really care for anything else, right? Oh, you know, missed a step there. We always need to add something to the, I should stop saying add. We always need to append something to that skew list. Whatever happened to the count, we need to append that, even if it didn't change. So if it's a C or a G, we have something to do. Otherwise, we don't need to do a check, because if it's an A or a T, we don't care. So it doesn't really make sense. I mean, you could do another LF to see if it's an A and another LF to see if it's a T. That's all fine, except whether it's an A or a T doesn't matter. You're just going to add whatever the current count is without doing anything to it. Right, so in our example, we get -1 to the count because it's a C, but then if it's an A, don't do anything, just put another -1 in the list and then another -1 in the list, right? So it would look something like this on that practice data, or the practice data, this cartoon example. And then on the 4th time through the loop, right, it's going to go up 1, so the count will change to 0 because it sees a G. Okay, and then it'll just keep on going along until it hits the end of this for loop up here. So that will get us the skew list. Then we need to create a list that will hold on to the minimum skews. So how do we do that? Well, something like, because it doesn't want to know the list, it wants to know the positions. So going back, look at the Roslyn problem. So it wants, those are apparently the positions where that GC is the most negative, G minus C is the most negative along that string. So let's call this position, man, I can't type. Position min skew equals, and it needs to be a list because, whoops, we don't want to have anything in there yet. It needs to be a list because there might be more than one position that has the same minimum. And then to get the minimum in a list is just like getting the maximum. So so if we say the min skew equals, we did this before for the max count, except we used max. Min works the same way. So the min skew is the minimum in skew list. Now, one trick here that we haven't really used before, It's very similar to the way you go through a dictionary with keys and values. You can do the same thing for a list, but there's something called enumerate. So if you do for I, comma, skew, and this is just like key value. I've just given it two variable names in my for loop. But to do this on a list, I need to use the enumerate. And right, this is going to work just like a dictionary would. So here, skew, let's just as an example, if I do skew 2, what would that output? Right, that would give me -1, right? 0, 1, 2. So it would be that value right there. So when I do for I skew and enumerate skew list, come on. I equals 2, skew equals -1. Right. So this is kind of like the dictionary notation where 2 is the key and -1 is the value. When I do it on a list and I use enumerate, I here is 2, right, matching that thing, and skew is -1, so that thing. And so why do I care? Well, right now we need to find the positions, which are I, right? I is the position in the list that minimize the skew. So we need to keep, we want to keep those two things together. Right? Because we want to do in this loop, if skew, oh, it's minimum. So we can just ask if it's the same as the min skew, right? Then what do we want to do? We want to keep that in the list of positions that have minimum skew, right? This list that we just initiated. So dot, we need to stick on the current position. Right, so in this case, position min skew ends as an empty list. Anytime the skew gets as low as the minimum, it's going to take the position of that in the genome, right? That's like 2 in this example. If that was the minimum, it would stick 2 into the list of position minimum skews. Okay. And that's, I think that's basically it. And then you just have to figure out how to, well, you've got to figure out the rest of that for loop to make that work. And then you've got to figure out how to print out this thing. Because what Rosalind wants is 53 and 97. Now, some of you might, actually, many of you, I think you've had to solve this problem already. There are lots of ways to print a list of integers. You know, the join command, lots of you have run into this problem trying to solve it. One of the previous, I forget if it was 15 or 16, but Roslyn doesn't like, it doesn't work, the join command doesn't work on lists of integers, right? So you have to figure out how to print a list of integers really pretty. There are some very simple ways to do it and some more complicated, but not terrible ways to do it. All right, so that's it for problem 17. Now, I promised we'd learn how to plot. So how do we, let me actually run that code on my practice data. So if you run that code on this DNA sequence, this is the correct answer, right? That's the positions. But in order to plot this, we need the whole sequence of skews. And so what that looks like, I'm going to write some code here. I'm going to call this my skew list equals that. Okay, and so this is pretty long. So this is if I run the code. That's the output if I tell it to just print the skew list. And that's what I need in order to generate the plot. Now, in your code, so because you've already, right, if you've gotten to this point to solve problem number 17, you've written this functioning code. You have the skew list right here. You could just stick a print statement in here, and which is what I did on my code, print skew list. Okay, that's fine. That's how I just got this thing. You can also, you don't even need to print it. You don't have to write new code. You can just stick the plotting function down here on the bottom of whatever code you're currently working on. So that's my skew list. And that's what I'm going to work on to get this kind of plot. So to plot in Python, there are a lot of really cool functions. We're barely even going to scratch the surface. I've given you a link here to matplotlib, which is a library of plotting functions. And this is already built in. If you're using Spider, it's all packaged in Anaconda. So we don't have to worry about adding a new package like we did for BioPython, but we do have to use import. So I'm just going to copy this. And I always put my imports at the top. So import that. Okay, so it's just telling me I haven't used it yet. That's fine. Now, just as a very simple, let's see if everything's working okay. I have a, very simple, just plot 1, 2, 3, 4, just to see how it works, make sure everything is set up okay. By default, if all I give it is one list of numbers, it's going to treat those as though they are the y-axis variables. And the x-axis variables are the index. So it's going to go, the expectation is from 0 to 3 as the x-axis and 1 to 4 on the y-axis. Whoops, I don't know why I did that. PLT, let's add a y-axis label. some numbers and see what happens if we run that. And this is one of the really cool things about Python Spider, is that it generates the plots in real time and shows them to you in this window. Okay, so everything's working fine. And like I said, right, it took the indexes 0 to 3 and plotted 1 to 4, but it also, the plot is, adds the trend line for you. So it connects the, well, it's not a trend line, it just connects the dots. You don't even see the dots. It just draws the line between the points. Okay. And that's a default function of plot. Like I said, so many ways you can tweak this if you just follow the documentation there to the PyPlot module. All right, so that's working. All we need to do is change the oops, that's jumping ahead. So instead of plotting 1, 2, 3, 4, right? We don't want to plot that. We want to plot the skew list. Okay, so not so hard, right? That's probably the easiest coding you've had to do in a couple weeks. And it's not some numbers anymore, it is the GC skew. Notice it keeps all of your plots over here, so you can pretty quickly scroll between different plots. Just another nice function. You know, ones you don't need, you can trash. Now that's all well and good, and where I started to skip ahead is that it won't always be the case that you want the line to connect every point along the array. And so I just have provided a couple of other functions that will allow you to, for example, play around with calculating a rolling mean. So let's import. This is another module, a package pandas, and this allows us to use PD instead of pandas. I'm typing that out every time. So if we import pandas, it's got a function that will do rolling mean for us. So I'm going to comment this out, this, and then we'll do in this example, GC is what we currently have called our skew list. So in my code here, doesn't matter whether you want to put skew list there or GC here, it doesn't really matter. Actually, I can just copy paste here. And so how do you know the syntax of all this? Well, it's all in the documentation. So this is probably, other than the name of the variable, copied out of the pandas documentation. So what this is saying is calculate the mean of the y variable. I could have named this. This is just a variable name, so I could have named that anything. But it's saying from the pandas module up here, use the series function on GC. I don't have a GC. It's skew list. And then series can take this rolling function and then it gives a window size. So this is going to calculate the average in 1,000 base pair windows. Well, my list is not that long. I'm going to say 5 and get the mean of that thing. So every 5 items in my Y variable list, it's going to get an average, and then take that as turn that into a new array that's called mean Y. Okay, and so actually let me go, I should have done this up here, because now instead of plotting skew list, I want to plot mean Y. So let's plot. And if I run that, so see my new, it's a little more wavy. Because it's averaging in 5 base pair windows. Now if I move that up to 10, so change my window size, smooths it out even more. What if I go to 15? Right, I start to see something that looks like maybe I have identifiable regions. Pretty cool. And then the other weighted averaging, there's some other examples here. I encourage you to play around with those. Again, just remember GC is the name of your variable, which in the example that I've been showing is called skew list. And these are functions that just take more complicated versions of averaging. Some of them, I can't remember, I meant to look this up earlier, but one of these may account for the fact that you sometimes, especially when you have a bacterial genome that is in fact circular, depending on where you start the search, right? We started it sort of artificially at 0, and you don't know where in the genome that actually is. So sometimes when you linearize a bacterial genome for the purpose of doing this kind of sliding window, you get artifacts at the end that don't belong there, because it should be continuing plus and minus as you loop around. And some of these methods of averaging are better at dealing with the artifacts you get when you run off the end. So up to that point, all we've been able to do is plot it to here. You can't run this code in a terminal because the terminal doesn't have a graphical output. There is something called X11 that you can, it's called port forward, and have it open a graphical window for you when you run it, but that's kind of beyond what we really need to do. Because if we needed to send this, one, we can save it right here. Spider makes that part easy. But if you were running this from terminal, you could just add plt.savefig and then give it a file name, and it will send this picture to a file. Okay, that's, and if you were running this on one of the supercomputers, which we'll probably start doing next week or the week after. I don't know if we'll get back to plotting things, but if we were running code over there and you needed to make a plot, you would have to save it to a fig, unless you go to the trouble of setting up some kind of windowing software, or what, I don't know, configuration of software. Okay, that's it for plotting. If you look at E. coli, so we run into this other problem, is that the minimum skew spot doesn't have frequent 9mers, right? So they didn't actually overlap very well. And so why is that? Well, it's because, you know, biologists maybe, you know, not maybe, it's not so surprising. And I've talked about it in class. I think I've mentioned it in the videos as well, that so far we've been matching exact patterns, but protein DNA interactions are not based on strict sequence complementarity, right? Proteins allow for variation in the DNA sequence that they bind to. So we don't understand the language of protein DNA interaction very well. And so it gets really hard to predict where the transcription factor binding sites are. We can find frequent words, but the next challenge is we want to allow for slight mismatches. So if the word is CTG that we think we're looking for, we want to allow for ATG or CAGC. Anyway, one base pair mismatches, for example. Okay, so the first step in doing that is to be able to compute the distance between two strings. So if you look at Rosalind problem 18, you're going to get two sequences that are equal length, and you just need to see how many of them differ. So we can kind of eyeball this. Let me blow it up a little bit. It differs at that position, scanning along, and then the last two positions. So the sample output is 3 because it differs at 3 positions. So how do you do that? Well, here's a little pseudocode, right? Just not even exactly pseudocode, but more like a strategy. And, you know, one hint is that sequence 1, position I, and then how do you ask if it does not match? This is the not equal operator. Here, sequence 1 and sequence 2 are what I would name these two things, right? That's sequence 1, that's sequence 2. And so I have to make a loop that changes I and slides along those. And then if I put I in both sequence 1 and sequence 2, it's going to match position by position and ask if they're not equal, add 1 to the distance, right? Because D is equal to the number of mismatches. So here this is asking, is it a mismatch? If it is, right, then add 1 to some counter, right? Or right, this initialized distance equals 0. That's the counter. Every time you get a mismatch, you're going to want to add 1 to that thing. And when it gets done, you just return the total for that distance count. And then the last one for today is 19, which is sort of going the other way. Instead of trying to figure out how many are different between two given sequences, now you're going to be given a sequence and then generate all of the potential patterns that are that distance away from it. So if you look at the sample output, what did it do? Okay, for A, it substituted CTG and it left the CG alone. Then it left the A alone and it had a C, so it substituted ATG. Then it leaves the A and the C alone, and on the G it substitutes A, C, and T. And then it includes the pattern that you started with, because it does not exceed D, right? So in this case, for ACG, D is 0. So it's included. Okay, that is a tricky one sometimes. People leave off the one that you started with. All right, so this example data set that they give is a little bit overly simple for this the problem itself, because it only asks for D of 1, but D could be anything. I think, yeah, so for this extra data set, this is the pattern that you start with, and D is 3. So you have to get all of the patterns that are up to 3 nucleotides away from that. So to solve the practice problem, or the practice data set where D is 1, that's kind of the first step. Because if you imagine that if D is 2, what could we do strategically? Well, we could take all of these things that we know are D equals 1 and then run them through that same function again. Because if I do another D equals 1 on top of CCG, I know that has to be D equals 2 away from this. So that's the basic overall, that's the overall strategy for this problem, is make a function, that's step 1 here, make a function that creates all the neighbors that are D equals 1 away. Okay, and then step 2 is create another function that calls that function D times, right? Just keep sending it back into that function until, you know, if it was D equals 2, you only have to send it back 1 time. If it was D equals 3, you have to create the D equals 1 list, send that list into the function again to get the D2 list, and then send the D2 list back in to get the D3 list. And you can imagine this list is going to grow really fast, okay? But that's why we let the computer do it. We just have to figure out the algorithm to make that happen. So it does have some similarities with what we had to do in pattern to number, right? So you're going to say something like, if what you see is an A, right? If the current letter is A, then substitute C, G, and T into that pattern. So we will work on this a little bit in class, but that's, you have the basic idea here. The only new thing is this extend versus append that I've noted at the end. So if the list is, the difference is if we have a list that has A and B in it, then if you'd use append to get these two things, then it's going to be A, B, and then the list CD as a single item. That because append only works on single items. So if you have a list and you're appending it to a list, the list gets stuck in as a single item. So you have to use extend to stick CD in as individual items. So then you would get A, B, C, D as individual items in the list. Why is that relevant? Because if you think about the way this is going to work, let me go back here and I'll add a new slide on here just so to help me illustrate. This is why doing this live is much better. So you may want to come to class on this one for sure. All right, if we start with ACG, these are all the D equals 1 patterns. In the program, it calls these neighborhoods. So these are the neighbors that are D is 1. Now, when I send this list into the D equals 1 pattern, I'm going to get a whole expansion for this one, a whole expansion for that one, and that one, and that one. Now, my CCG list is going to be this long, right? A 3mer that is 1 away from CCG is going to give me another list. If I need to collect all of those, I don't want it to stick another list in here that has all the CCG patterns, right? I can't do this completely, but it would have CCG, TCG, and so on, all in a list inside the list, and we don't want that. We want these stuck on there as their own items. And we have to have that, right? Because now if we need color code these are from the feeding this back in. So now these are the ones, actually I shouldn't, just to avoid confusion. Let's say this is GCG, TCG. Those are all the things. These are another 1 away from that. And yes, you're going to get duplicates, especially when it's a 3 base pair motif, and you start getting 2 or 3 away. There's going to be tons of overlap here. Okay, so if you want to get the unique ones, you're going to have to use set to get the set. All right, that's also, talk about that right there. But okay, so these are generated by D equals 2. These guys were from D equals 1. If I have to go D equals 3, I can't have these in their own list inside the list, or otherwise my loop that goes through here is not going to know what to do with that. So that's why you have to use extend. Once you generate all the D equals 2, then you extend the neighbors list to include those so that you can put that into D equals 3. and so on. Okay, so obviously you're going to need to have a counter that counts how many steps you've gone. So that's hopefully that's enough to get you started, well, at least in conjunction with this kind of strategy. Okay. I think that's it. All right, so should be up to problem 19, hopefully before Thursday. And like I said, we'll talk more about 19 in class today. And hopefully and also troubleshoot any problems you've had up to this point. Okay.